Molecular geometry going to be the topic of this lesson, and we'll start with a discussion of VSEPR theory, which is kind of the foundation for our different molecular geometries, and then we're going to go through all the different electron domain geometries and molecular geometries for 2, 3, 4, 5, and 6 electron domains that most of you need to memorize, and then also show you how you go from a Lewis structure and know which corresponds to it. My name is Chad, and welcome to Chad's Prep, where my goal is to take the stress out of learning science. Now, in addition to high school and college science prep, we also do MCAT, DAT, and OAT prep. You can find those courses at chadsprep.com. Now, this lesson is part of my new general chemistry playlist. It's an entire year of general chemistry. I'm releasing several lessons a week throughout the school year, so if you want to be notified every time I post one, subscribe to the channel, click the bell notification. So let's dive in here, and we'll start again with that discussion of VSEPR theory. And if you look at it, it really should be VSEPR theory, but that just kind of sounds dumb, so we say VSEPR theory, but it's valence shell electron pair repulsion. And so the idea is that electrons are negatively charged, and so whether we have bonding or non-bonding electrons around some sort of central atom in a compound, they want to spread out as far as possible to minimize the repulsion between them. So the further they are, the less repulsion they're going to experience, and that's going to keep their energy low, which we associate with stability. So this is kind of how we explain the different shapes, is we're going to look at the number of different electron groups around an atom, and we'll call them electron domains. And these electron domains are either going to be an atom we're bonded to, and it turns out it won't matter if it's a single, a double, or a triple bond, but just an atom that the central atom is bonded to, or a non-bonding pair of electrons. And those groups will spread out as far apart as possible. And we're going to deal with 2 electron groups, 3 electron groups, 4 electron groups, 5 electron groups, and 6 electron groups, which again from here on out we'll call electron domains. So, and you're on the hook for understanding the geometries associated from 2 to 6 electron domains. So we'll start with 2 electron domains, and when you've got 2 electron domains, for them to spread out as far apart around that central atom as possible, they're just going to be on opposite sides, and they're going to be 180 degrees apart. So here we'd refer to this bond angle as being 180 degrees apart, from bond to bond, 180 degrees, and we refer to this molecular geometry as linear. Now, for 2 electron domains, it turns out that molecular geometry and electron domain geometry, they're going to be the same thing. So, but we're going to start with electron domain geometries, and then we'll move on and talk about a special class of molecular geometries that are kind of derived from there. So, with 2 electron domains, it's going to be linear for the electron domain geometry, and it turns out also for the molecular geometry, we'll see the distinction between those for larger numbers of electron domains. Now, for 3 electron domains, it turns out the farthest you can put 3 things apart. It turns out it is a planar structure. It's a 2-dimensional structure. It's like in the plane of the board here. And essentially all you have to do is take 360 degrees around the circle and divide it into 3 parts. So you get 3 equal bond angles, and 360 over 3 is 120 degrees. And if you look, these kind of form the corners of a triangle. And so they kind of name the shapes. They try to make sense out of them based on where the outside atoms all are. And so with the 3 corners of a triangle and in a single plane, a 2-dimensional shape, they call this trigonal planar. All right, 4 is where things get a little bit complicated because it's no longer 2-dimensional. If it was 2-dimensional, we just take 360 degrees again and divide it by 4, and we get bond angles of 90 degrees. But it turns out, by adopting a 3-dimensional geometry, instead of occupying a single plane, we're going to spread out into 3-dimensional space here. We can spread those angles out from 90 up to 109.5, it turns out. And so if you look here, so to draw a 3-dimensional shape on a 2-dimensional surface, we have some conventions here, and we call this a wedged bond right here, and it's supposed to represent an atom here that's coming out of the board towards you. That's why I've drawn the atom B here very large. And then we've got this dashed bond right here, which is supposed to represent something going into the board away from you, and that's why I've drawn this really small, because it's further away from you than the other atoms here and stuff. So if you take a look at this shape here, you can kind of see that these 3 form the bottom of a pyramid, and they all kind of go up towards the top of this pyramid. And it turns out this pyramid shape is called tetrahedral. So, and this pyramid is a tetrahedron. Now you should realize that, again, all the angles here are 109.5 degrees. not 90 degrees. And it doesn't matter which of these two I chose. I chose these two because they're in the plane and it's easiest to see, but I could have chose these two. The angle between these two bonds is 109.5. The angle between these two is 109.5. The angle between these two is 109.5. The angle between these two is 109.5. All the angles of any two of the bonds are 109.5 degrees. So, and the temptation is to look at this Lewis kind of structure and think, oh, if they're next to each other, they're 90, and if they're opposite from each other, they're 180, but that's not true. The three-dimensional shape of this tetrahedral here is that all the bond angles are 109.5, period. There's no 90 and 180, so it doesn't matter which two you choose. They're all 109.5. Okay, so this is up to 4 electron domains. So we can also deal with both 5 and 6 electron domains, but that's going to require an expanded octet. And so some of you aren't going to be on the hook for these, but that's going to be the vast minority of you. The majority, you are going to be on the hook for 5 and 6 electron domains as well. And so if we see the way this works, so you're going to have 3 of the 5 forming a triangle around that central atom, kind of in this horizontal plane. So this is hard for me to draw because I am artistically challenged, but that's kind of a triangle formed around this, in this horizontal plane around that central atom. And then you're going to have one above and one straight below. And what you'll find is that these 3 that formed a triangle form a pyramid with the top one, and so that would be a triangle-based pyramid. And then they also form a pyramid that's inverted with the bottom one as well. And so what you end up with is one pyramid on the top facing right side up and one pyramid sandwiched up against it facing down. And so it's 2 triangle-based pyramids, one right side up, one upside down. But we end up calling this, therefore, trigonal, I can't spell apparently, bipyramidal. Or you might hear people say bipyramidal. I really couldn't tell you which one's correct, but trigonal bipyramidal or bipyramidal, same diff. Cool, and again, it makes sense based on the shape here with 2 triangle-based pyramids that we'd call it such. So then we move on to 6 electron domains here, and it's going to be somewhat similar to this. And one straight up, one straight down. And again, these 4 across the middle here form a perfect square that's once again in this horizontal plane. So, and then you have one straight up and one straight down. Cool. Now, it would be nice if they called this like square bipyramidal to be consistent with what they did here, but they don't. So it turns out we refer to this as being octahedral. So, and it turns out that comes from the name of the shape. So octahedral actually means 8 faces. And if you kind of look, all of these, so we formed a triangular face right here. We'll form another triangular face out here. We'll form another triangular face out here, and then there's one on the back side. So there's, on this top pyramid, there's 4 triangular faces. And then on the bottom pyramid, you'd end up with another 4 triangular faces. And so it has 8 triangular faces, hence 8 faces being the name here, octahedral. So don't get fooled by octa here. There's only 6 electron domains when it's octahedral. Now, bond angles for these expanded octets are a little bit complicated because they're not all the same. So, but it turns out octahedral is a little easier to deal with because if you take any 2 that are next to each other, so they're 90 degrees apart. So notice, like in this plane, we're just splitting these 4 things up around 360 in that horizontal plane, and they're all 90 degrees apart. But if you pick 2 that are opposite each other, or top and bottom, or any 2 that are opposite, it's 180. And so we end up with 2 sets of bond angles of 90 and 180. So you pick any 2 adjacent ones, 90, pick any 2 opposite ones, 180. Gets even a little more complicated for the trigonal bipyramidal, so I saved it for last here. So, but these 3 that are in the triangular plane right in the middle here, you pick any 2 of those, and you're going to get bond angles of 120. So, however, they're in the horizontal plane, and this guy's in the vertical plane, and so if you pick any one of these 3 with him, it's going to actually form a right angle and be 90 degrees. And again, he's got a right angle formed with this one and this one as well, because again, they're in the horizontal plane, he's in the vertical plane. But then you could also say, well, relative to the one that's immediately opposite him, that would be 180 degrees. And so most of the time you see this defined as three sets of bond angles, 90 degrees, 120 degrees, and 180 degrees. And these are the 5 electron domain geometries you're on the hook for. Now, it turns out we can actually go past 6 electron domains. There are different structures that do exist with more, just not going to be on the hook for them in a typical general chemistry class at all. So we'll stop at 6. That means you just got to know 5 different electron domain geometries: linear, trigonal planar, tetrahedral, trigonal bipyramidal, and octahedral, which apparently I erased an A here. Cool. Not only are you on the hook for knowing their names, you also got to know the bond angle. So again, 180 degrees, 120 degrees, 109.5, which you really, really need to get this one down. This one's asked really commonly. 90, 120, 180, and then 90 and 180. These are the 5 foundational electron domain geometries. And in a little bit, we're going to talk about molecular geometries, and they're all going to be derived from these lovely shapes. And what we'll find out is that if you start replacing any of the atoms, and not really in this one, but I guess in the rest, if you start replacing any of these atoms with non-bonding pairs of electrons instead, we'll still give it the same electron domain geometry name, but the molecular geometry, which is really based on where atoms are located, not where non-bonding electrons are located, and since we'll be missing an atom and have a non-bonding pair instead, the molecular geometry is going to get a different name. And so if around the central atom you start putting lone pairs, that doesn't change. Again, as long as you just count up the total number of electron domains, 2, 3, 4, 5, and 6, the electron domain geometries, you know those 5. But the molecular geometries are going to get a little more complicated. We will find out, though, is that if all your electron domains are bonding domains, then your molecular geometry is going to have exactly the same name as the electron domain geometry. But if you start replacing any of these atoms with non-bonding pairs of electrons, your molecular geometry will get a different name than the electron domain geometry. Let's have some fun and take a look. All right, so we're going to start with 2 electron domains, and I've drawn 3 different Lewis structures up here, and I just want to give some variety here, but we really don't have any options for 2 electron domains. It's just going to be linear no matter what you do, and it's linear here, it's linear here, and it's linear here. And so what you should realize is that with 2 electron domains, your electron domain geometry is called linear. But your molecular geometry is also going to be called linear. So these are going to be in a straight line here. And so notice in beryllium's case here, we've just got a single bond on both sides, and that would be considered 2 electron domains because beryllium is bonded to 2 atoms and has no lone pairs. So if we look at the central atom here, carbon's bonded to 2 atoms. And notice it doesn't matter that we've got a single bond on one side and a triple bond on the other side. It's not the number of bonds necessarily, but the number of atoms the central atom is bonded to. And it's bonded to 2 atoms, and that central atom has no lone pairs himself. So that's 2 electron domains. And again, that means the electron domain geometry is linear, and they're both bonding domains. So that means the molecular geometry here is linear as well. And then finally, in the case of carbon dioxide, again, it's just bonded to 2 atoms. They're double bonds this time, but that, again, whether it's single, double, triple, that's just a single electron domain, counting an atom you're bonded to. And so it's bonded to 2 atoms, and then carbon has no lone pairs for a total of 2 electron domains. Once again, that means the electron domain geometry is linear, and the molecular geometry is also going to be linear. So I just wanted to show you some variety that, you know, single bonds, double bonds, triple bonds all count as 1 electron domain each. So it really is just the number of atoms the central atom is bonded to, not necessarily the number of bonds that it's making. Cool. We'll start to see some variety, though, when we go to larger numbers of electron domains. Let's take a look. So now let's take a look at 3 electron domains. And we said this earlier, when you've got 3 electron domains, your electron domain geometry, or EDG for short, is trigonal planar. So, and I've got 3 examples here. And so in this first one, the central atom is boron, and it's bonded to 3 other atoms and has no lone pairs, a total of 3 electron domains. So for the second one here, the carbon here is bonded to the central atom. He's bonded to 3 other atoms and has no lone pairs. So once again, and then finally, this last one, though, is going to be a little bit new here. So the central atom sulfur is only bonded to 2 atoms, but then has a non-bonding pair of electrons. And once again, that's still 3 electron domains. And so all of these would be defined as having an electron domain geometry as trigonal planar. So what we'll find out is that for the first 2, since all 3 electron domains are bonding, the molecular geometry is going to have the same name. But when your central atom has any lone pairs and has a non-bonding domain, so if any of those electron domains are non-bonding, molecular geometry is going to get a different name, and we'll see why here. So in this case, our molecular geometry, sometimes called the MG for short. In this case, trigonal planar. The second case here, also again trigonal planar, same as the electron domain geometry again, because all three electron domains are bonding in both cases. And sometimes we'll go ahead and redraw the Lewis structure. Lewis makes everything look like it's either 90 degrees or 180 degrees. It looks like these two are 90 degrees apart, and it looks like these two are 180 degrees apart. Well, the truth is no. Knowing that it's now trigonal planar, we'd know that all the bond angles are 120 degrees, and so we might draw a structure better representing the molecular structure from here on out. So, but again, Lewis says, oh, everything's 90 or 180, the way I draw them. So, but the truth is, again, we have to now factor in some different things we know about the molecular geometries and electron domain geometries based on the number of domains. Now, in this second one here, we might do the same thing and spread this out a little bit to represent that trigonal planar structure. But one thing you should know is here we've got a double bond to the oxygen. So, and that means there's 4 electrons there, not just 2 like there is here and here. And so there's more repulsion going on from 4 electrons than there is from 2. And what's going to happen is because we're going to repel these 2 bonds down further, according to VSEPR theory here, that this angle right here is going to be a little greater than 120 degrees. And same thing with this one here, a little greater than 120 degrees, and then that's going to force these two to be, or these two to be closer, and this angle to be a little less than 120 degrees. And so you should know that pi electrons, when you have like a, I don't want to say pi electrons, we'll learn about that a little bit, but when you've got a double or triple bond, it's going to typically lead to greater repulsions in a structure like this, and so the bond angles aren't going to be exactly 120 in this case. We'll also find out that lone pairs here in a sec are going to have a similar effect. So we'll take a look at SO2 here. And so for SO2, if we were to draw a similar representation to kind of take into account the shape here, because these oxygens aren't 180 degrees apart, turns out they're roughly 120 degrees apart, based on what we know about the trigonal planar electron domain. Cool, now it turns out that lone pairs tend to lead to a greater repulsion than bonding electrons. And in this case, this bond right here, this angle between the bonds is probably not exactly 120. And truth is, it's probably slightly less than 120 degrees. Now, you might be like, well, Chad, there's double bonds there. What about what you just said? Well, that's true, but it turns out lone pairs usually have a greater repulsion. And so I couldn't tell you what the exact bond angle here is, but it's probably ever so slightly less than 120. And one thing you should know, when I say slightly less than 120, it might be like 118. So it's not a huge difference, usually a couple of degrees kind of a thing. Now, if we look at molecular geometry, and we haven't put a name on it here, but what I can tell you is that the molecular geometry here is not going to be called trigonal planar. So, because we don't even form a triangle in the same way from the outside atoms. And in this case, if we look at the shape, when you've only got 3 atoms in your total in your structure, you've got 2 options. It's either going to be all straight in a row, which we learned to call linear, or they're not going to be in a row, which case we'd call it bent. And so in this case, this molecular geometry is called bent. And the idea again is that, when we had 3 atoms, 3 outside atoms forming a triangle, trigonal planar. So, but now when one of those atoms is not there, again, for molecular geometry, we look at where the atoms line up, not where lone pairs of electrons line up. And these 3 atoms, again, are either linear or they're bent. And in this case, they're definitely not 180 degrees apart linear, so they are bent. We'll see this gets even a little more complicated as we get larger and larger numbers of electron domains. So let's take a look at 4 electron domains. All right, so with 4 electron domains, your electron domain geometry is tetrahedral, and all 3 of these examples have 4 electron domains. In the case of CH4 here, they are all bonding domains. In the case of NH3, there's 3 of them that are bonding domains, and then 1 non-bonding domain. And then in the case of water here, H2O, we've got 2 bonding domains and then 2 non-bonding domains. And so for the first one here, because all 4 electron domains are bonding, the molecular geometry is going to get the same name as the electron domain geometry and be called tetrahedral. So, and you'll find out, especially if you take organic chemistry, that we get, pretty involved in drawing accurate 3-dimensional portrayals of these molecules. And so if we kind of match this up with what we did earlier, you could kind of draw something along the lines of that. Cool. So, but most of you aren't going to be on the hook for something like this when we start getting three-dimensional here. You're probably just going to go with Lewis. But again, one thing I really want to point out and focus on again is that if I say what is the bond angle between these two hydrogens, or at least the bonds for those hydrogens, it's 109.5. And if I say what's the bond angle between these two, don't say 180. Again, all the angles are 109.5, regardless of what Mr. Lewis says. Mr. Lewis makes everything either look 90 or 180, but you have to take what you've learned now about electron domain geometry and molecular geometry to know what the real bond angles are. What's the angle right here? 109.5. What's the real angle right here? 109.5. Okay, so now we're going to put a lone pair on there, and that's going to change a couple of things. So one, again, it doesn't change the electron domain geometry. With 4 domains, it's still tetrahedral, but it is going to change the molecular geometry. And so first thing we'll do is we'll draw the shape here, try and represent it, and we're going to have a hydrogen here, here, and here, and then the lone pair of electrons. And if you connect all the atoms here, what you're going to find out is that you still got a triangle base, but then kind of the only other atom is the nitrogen. So going up to that nitrogen, well, if it was going up to another hydrogen like we did here, you'd have a nice, you know, full pyramid, if you will, and it'd be a tetrahedron. But now it's kind of a flattened pyramid, because instead of capping up here to another hydrogen, it's just going up to the nitrogen, which is much shorter in the one dimension. And so this is not a tetrahedron. A tetrahedron is the same in all dimensions. And so in this case, it turns out that the molecular geometry is going to be called Trigonal Pyramidal, or Pyramidal, again, depending on who you talk to. And so it's a triangle-based pyramid, but again, it's not a perfect tetrahedron because it's not the same in all dimensions. It's kind of like a flattened pyramid, if you will. And again, we call that trigonal pyramidal. And so this is ammonia, it turns out, NH3. And if somebody says, hey, what is the electron domain geometry of NH3? You're supposed to say tetrahedral. But if somebody says, what's the molecular geometry? You're supposed to say trigonal pyramidal. You're also supposed to know, again, that the lone pair gives greater repulsions to the other electron domains than they give to each other. And so as a result, this is going to kind of flatten these angles down a little bit. And so this angle right here, instead of being 109.5, is going to be ever so slightly less than 109.5. And it turns out it's actually right around 107 degrees. So you don't actually have to know that it's 107. The only reason I put it up there is that, again, I want you to know that when I say less than 109.5, I don't mean like 50 or 90. I mean like 2.5 degrees, like 107. So it's just a couple of degrees, this difference. But you should know that it's not exactly 109.5. They're exactly 109.5 here in CH4, but here the bond angles are just slightly less than 109.5. And again, you're not on the hook for knowing it's 107. You're on the hook for knowing it's just slightly less than 109.5. Moving on to water here. So in water here, a lot of students look at this and they think, oh, those hydrogens again are 180 degrees apart. Well, again, they're not. All the angles, no matter what two atoms you choose, and we only have 2 atoms, is roughly 109.5. But once again, it's not going to be exactly 109.5 because the lone pairs are going to change things. You might be like, well, Chad, aren't those lone pairs opposite each other? Well, again, those lone pairs are roughly only 109.5 degrees apart, regardless of what Lewis makes them look like. If we actually draw a better representation of the geometry in water, you'll often see us represent it like this. And this angle, again, right here below, between the bonds, that bond angle is going to be less than 109.5 degrees. And again, just slightly less. And it turns out, if you cared, it's actually like 104.5 degrees, which again, you're not typically going to be on the hook for. But what I wanted to show you, though, is that now that I've got 2 lone pairs, there's even more repulsion. It's going to push those hydrogens closer together so that now it's even another 2.5 degrees lower at 104.5 degrees. And so big thing takeaway is that you're supposed to realize that when you put lone pairs on the central atom, it's going to lower the bond angles usually by just a little bit. And so sometimes you get a question that says, which of the following has bond angles of exactly 109.5? Well, he does, and NH3 and water don't. So, but if I said which of these 3 has bond angles that are just slightly less than 109.5, well, now NH3 and water do, whereas CH4 does not. Cool, so that's 4 electron domains. Let's go now to our expanded octets and take a look at 5 electron domains. So with 5 electron domains now, reminder that the electron domain geometry is called Trigonal Bipyramidal or Bipyramidal. And now we've really got 4 different options for molecular geometry. So we can have all 5 electron domains be bonding. We can have 4 bonding and 1 non-bonding. We can have 3 bonding and 2 non-bonding. Or we can have 2 bonding and 3 non-bonding. So, and there's something funky, it turns out, about the trigonal bipyramidal shape. Where you put the lone pairs is going to matter. Not all 5 positions, it turns out, going around are equivalent. And so we'll remember something about that. So with this first one, life is not so bad. The molecular geometry here. So because all 5 domains are bonding, it should get the same name as the electron domain geometry, and that is totally true. And so our molecular geometry is still trigonal bipyramidal. Cool, and the angles are either 90, 120, or 180, just like normal. Now, here's the deal. So if you recall, these 3 kind of form a triangle in the horizontal plane, and then you have these pointing straight up and down. Well, it turns out they get special names. For the ones that point straight up and down, they are referred to as being axial. And so if you look at like your, if you know your anatomy, your axial skeleton is the skeleton that runs right up the vertical of you, includes like your spine and your skull and stuff like that. So so these 2 are referred to as the axial positions. They're 180 degrees apart. So, but then you've got these 3, so right here in the middle, that kind of go around the equator of the molecule, if you realize. And so they're often referred to as being equatorial. Well, if you recall, we said that lone pairs of electrons give off greater repulsion than bonding electrons. And so when we get to starting to put lone pairs around the central atom, where they go actually matters with these 2 different positions. And so it turns out they're going to preferentially go in these equatorial positions so that we can minimize the repulsions. So they're going to experience less repulsion when we put them equatorial than as if we put them axial. And so you've got to know, and it's going to affect the molecular geometry and kind of the shape it actually adopts, that when we start putting lone pairs in, they're going to preferentially start adopting these 3 positions, not the axials. And so notice once we go to 1 lone pair, it had to just go in one of these 3 positions. To 2 lone pairs, again, it had to go into 2 of these 3 positions. And then with 3 lone pairs, all 3 equatorial positions have the lone pairs. The axials still get the atoms. So super important that we know that, and this is only something to worry about for trigonal bipyramidal electron domain geometry, so 5 electron domains. Now, visualizing this here, so if you kind of take this right here and turn it sideways, so you'll find out that these 2, again, are 120 degrees apart, but then these are going to form like a tabletop surface. So these would be like the legs of the table, and this would be like a tabletop surface looking like a sawhorse or a seesaw, depending on who you talk to. And so it goes by both names. You can call it seesaw or sawhorse. Cool, so you could kind of envision it turning sideways and you put one kid on this end and one kid on this end and they're just teeter-tottering back and forth like a seesaw, if you will. Or it's a sawhorse, kind of that tabletop surface with a couple of legs, although most of the sawhorses I deal with have 2 sets of legs, but whatever. Goes by both names. That is the molecular geometry associated with having 5 total domains, but 4 are bonding and 1 is non-bonding. Okay, moving on to the next one here. Again, now 2 of the equatorial positions have lone pairs. And if you look here, we know that these 2 chlorines in the axial positions are roughly 180 degrees apart. And then this guy's in the horizontal plane. And so if these are in the vertical plane and he's in the horizontal, they should be 90 degrees apart here and 90 degrees apart here. And again, these are 180 apart from each other. And if I turn this sideways, I'd say they form the perfect letter T. And that's exactly what we call this. We call this T-shaped. So again, the electron domain geometry for all of these is trigonal bipyramidal, but the molecular geometry is going to get a different name if there are lone pairs on that central atom. So again, trigonal bipyramidal when all of your electron domains are bonding. So with 1 non-bonding, 4 bonding, seesaw or sawhorse. With 3 bonding, 2 non-bonding, T-shaped. And then this last one here, so this one will be important. I'll allude back to this in a later lesson in this chapter. So for this one here, all 3 equatorial positions are lone pairs. And so we just have these 2 fluorines and the xenon. And in this case, with 3 atoms, we said this earlier, with 3 atoms, they're either in a straight line and we call it linear, or they're not in a straight line and we call it bent. Well, in this case, these in the 2 axial positions, they really are 180 degrees apart. And if they really are 180 degrees apart, then this is going to be called linear. And so this is the second electron domain that we're seeing called linear here. So earlier we saw that there were two different molecular geometries that were called bent, one with 3 total electron domains and one with 4 total electron domains. And now we're seeing that there's 2 different molecular geometries called linear as well that are possible. Okay, so that's 5 electron domains, and now let's get ready and move on to 6 electron domains. So now we've got 6 electron domains, and our electron domain geometry is going to be octahedral for each of these. And we're either going to deal with all 6 electron domains being bonding, and again, if all your electron domains are bonding, then your molecular geometry gets the exact same name as the electron domain geometry. So in this case, SF6 here is going to be octahedral. So, however, in these other two, IF5 here, which has 1 lone pair on the iodine, and then XEF4, which has 2 lone pairs on the xenon. So they both still have 6 total electron domains, but here 5 bonding, 1 non-bonding, here 4 bonding, 2 non-bonding, and the molecular geometries are definitely going to have a different name than the electron domain geometry. So these are not going to be called octahedral for the molecular geometry. And it turns out, if you take a look at this one right here, so, and again, it turns out with octahedral, this is different than trigonal bipyramidal. It turns out all the positions are equivalent. There's no like axial and equatorial, because if you just turn this thing 90 degrees, then what would be axial would now be equatorial and vice versa, and all the positions are equivalent. So this is different than trigonal bipyramidal in that case. So if you put on 1 lone pair, it doesn't really matter where you put it. So I just chose to put it down here. I could have put it up here or in any one of these positions as well, but it's easiest to see the shape here. So you can kind of see that, again, these are the 4 that are kind of in that horizontal plane forming a square, and then they kind of form a pyramid all towards this one up here. And so it's a square-based pyramid, and so the molecular geometry is actually called square pyramidal. Or again, square pyramidal, depending on who you talk to. Okay, now when you go to 2 lone pairs, the big thing you do need to remember, though, is that those lone pairs experience the greatest repulsion. And so you don't want to put them only 90 degrees apart. You want to make sure you put them 180 degrees apart. So going back to the basic shape, I chose to put top and bottom, but I could have chose these 2 to be the lone pairs, or could have chose these 2 to be the lone pairs, and it would be the same thing regardless. But you'll definitely most commonly see it drawn this way, but you definitely just have to make sure those lone pairs are drawn on opposite sides 180 degrees apart. And so the 4 outside atoms that are left just form a perfect square. And this is actually a 2-dimensional structure for the atoms. It's just a square all within a single plane, and so we call it square planar. Cool. And we have now done an example of every single molecular geometry you are on the hook for. So you need to memorize all of them. So you need to be able to look at a Lewis structure and count the number of electron domains. And right off the bat, that should tell you the electron domain geometry. And then you should be able to look and say, okay, well, how many are bonding, how many are non-bonding, and therefore identify it further and get the correct molecular geometry as well. So definitely some memorization here. You're on the hook typically for all of it. They could give you any sort of Lewis structure and then ask you the molecular geometry. They could also take this a step further. They could also just give you the chemical formula like XEF4 and then expect you to draw the Lewis structure so that you can determine the molecular geometry or the electron domain geometry. And so you want to get really good at these Lewis structures from the last chapter. So because oftentimes they're going to be the first thing you have to do in answering a question on molecular geometry as well. Now, if you found this lesson helpful, then hit that like button. And if you like puppies, then you should hit that like button as well. Or if you just want to help me, let YouTube know that they should be showing this lesson to other students as well. If you are looking for practice material on molecular geometry or anything else in your general chemistry course, I've got quizzes, chapter tests, practice final exams, over 1,200 questions in total in my general chemistry master course. I'll leave a link in the description. A free trial is available. Happy studying.